everyone. I'm Vincent, and I'm going to introduce Project TReC. So the name is Interpretable Hybrid Modeling of Orbital Dynamics using Kolmogorov-Arnold networks. So a bit of context. The project originates from a newly established kind of neural networks they call Kolmogorov-Arnold networks. So the main idea here, is instead of learning like the weights and a fixed activation function, you have learnable activation function. And this brings a very nice property for this kind of networks, is that you can have interpretable functions. Thank you. You can have interpretable functions, and you can build up on them to build even more complex functions by adding some layers to your network, basically like this. And a very nice property is that you can use that to learn physics laws. And this brings to mind the first thing of physical systems. I don't know if you remember, but at that time, like it was like 10 years ago, Google DeepMind and Microsoft made like a big warm-up in the physics community because theorists like were a bit alarmed that you can learn physics law and you basically don't need them anymore. That wasn't true at the time, but this brings us this to mind. So at the time they were using graph neural networks. Then came the physics neural networks, where you bring basically physics law in the forms of differential equations. Okay, so animation are not working. Sorry.
Sorry, with the other road then
No, sorry, no animation. So basically, you put differential equations into the loss function, and by using that, you are able to understand physics and have some guidance. You can get simulator out of AI. But the main drawback here was that they were not easily interpretable, even though you learn physics. So in 2024 came the new CANs that came as a new breakthrough because now it's directly interpretable, and you can build upon that, and you don't need humans to put physics law into the equation, so physical intuition, you can directly learn from data. So we kind of agree in our team that we should try them, and we should try them on a sufficiently complex framework so that we can reproduce it and have a framework that can translate to similar problems. So basically we build up a list of what's relevant. We need a problem that involves the differential equations, so the language of physics, basically. Complex functions to learn, an incremental problem, so it should not be very hard from the beginning. You should build simplification and then add up to have an increasingly difficult problem. And we need, of course, some expertise in the physics behind to guide and interpret what's going on. So our ideal candidate was orbital mechanics. So basically here you have an expression of the total acceleration undergo by a satellite orbiting the Earth. And you can basically build very simple simulator by using just the Earth gravity. And you can build up by adding that the Earth is not really a sphere. You can add the atmosphere, you can add external bodies, gravity, and you can also add the sun pressure and the satellite thrust. So you can basically build up on that, and that was really a good thing to start with an easy problem and go for a very hard one at the end. So just, I won't go into the details here, but just so you know, here are the expressions of basically some expressions. You see that we have a term to the v squared. We have the atmospheric pressure that can be a very complex model to learn, so that's a good thing. If you build up on the solar radiation pressure, of course, when the sun is hidden by the Earth and the satellite is behind, you don't have the effect of the sun. So basically, you have a shade factor here that might be difficult to learn, so that's a good thing. And you also have like complex expression depending on all three axes. That is quite challenging to learn too. So basically, our question is, can networks learn nonlinear perturbation forces in orbital dynamics while remaining interpretable and physically consistent within a hybrid framework? So our objective will be to validate a homemade simulator that we call an orbital propagator. So that starts from initial conditions to some orbits around the Earth. Build a dataset of simulated trajectories. So of course, if you have a simulator, we can build any trajectories, any orbiting body. We can add complexity in them, and so build different datasets. Of course, develop CAN-based modeling frameworks, and in the end, analyze the interpretability of the components that we have learned. So here you have a picture of some kind of orbits that we try to simulate. Our team is composed of 3 members right now. Also, that you will see him at noon for the workshop. Myself, Vincent, and Ahmed. We are all working at Multitel, and we have different backgrounds, as you can see, going from more applied mathematics to physics and software development. So here's the breakdown of the workshops, of the work package. I won't go into the details, but know that we have different tasks that could be highly parallelized. So that's a good thing because we can work on different problems with, the same goal, but with different complexity. Some can work on maybe the drag components, other can work on the fact that the Earth is not a sphere, and we can gather together the whole thing at the end. For us, that's an important thing to have at the summer project. One thing that might be a bonus that would be quite cool, at the end, if we have a demonstrator and a validator that works, we will try to replicate the orbit of famous satellites, so Hubble, the ISS, Galileo. So that's quite cool. I should have a demo here, but I guess. Oh, okay. Great, sorry, it works. So you have here a 3D view of an orbital propagator that we've done prior to this work. So basically, you can start with some parameters. You propagate, and you have a simulation of how the satellite should behave. You have the moon direction, the sun direction, the Earth, the imprints, and of course you have a lot of plots showing all the altitude is changing with time, the speed, and so on. And so we will use this tool a lot to basically add perturbations to our simulation and build up some data. Okay, so the effects we solved are basically machine learning, AI, any related skill in that area. If you know physics and aerospace, orbital dynamics, numerical simulation, that's a plus, but that's not mandatory at all. Software engineering, that would be quite good for any data processing, any data pipeline, anything that could interact, and probably a demo at the end. So by joining us, you will learn new frameworks, new architectures, how we can train neural network on incrementally difficult problems, how to prepare data for your training. A visually appealing demonstrator will be built at the end. The basics of orbital dynamics, that's quite cool. You should not learn that everywhere, basically. So, and if everything goes well, publication and eternal glory, of course. Do not hesitate to contact us by mail, and if you want more info, we have here a QR code to our repository. And that's it. Thank you.
Thanks.
And of course, if you have questions.
Yeah, thank you.
Please.
Any question? Just one quick. We already understand how it could be applied to orbital dynamics. In any case, then anyone would like to come with another use case using the same network. Do you have in mind any use cases that could benefit from CAN-based architecture? And how flexible are you?
The goal is really to build expertise and to understand what will go wrong, because something will go wrong, and that's the whole purpose of it, is to learn how to deal with those problems and to really learn from the theoretical point of view, so from the paper, or you can really go into an implementation that works. And basically, you have to have an example, so a demo and some physics behind. And in the end, if that works, as expected, I would say, we can build upon that and basically use the framework, like general framework. You come with a problem, and we will tell you how to prepare the data, and so on. So it's really from scratch, from the paper, theoretical aspects, to a visually appealing demonstration at the end. So,
okay, so you're yes.
I think yes.
Right. Thank you.
Thank you.